Hello everybody and welcome back to another stream. Today I'm going to be building upon one of our past challenges. I think it was the fourth one where we completed Dijkstra's algorithm, or a pathfinding algorithm in C++. And in that algorithm we used a very simple representation of a map where we essentially just had a 2D array and the weights of the distances between two nodes was represented just by elements in the array, and that was not very efficient or practical. I mean, it kind of was efficient, it did simplify a lot of the code, but it would not be used in any practical manner in the next level program. So today, I'm going to try and build upon that, and we're going to have to create a node class that will allow us to represent this code in a more structural and a more practical manner. So let's go ahead and get started. So today we're going back to the Minecraft soundtrack. It's been a bit, but you know what? Who knows? Okay. So in our challenges, I'm just going to go ahead and copy over the Dijkstra project to a new folder, just because we're essentially going to be using the same code, just building upon it. And I'm going to open that project up. So, solution. Alright. So what we ended up with last time was essentially this representation of a map, which essentially translated to this over here, where the distances between two nodes were represented by weights. And obviously this won't be the most efficient or the most it won't be too easy to generate in a real world environment. You're more likely going to have a class to represent each node if you were to put this in a real world application. So we're going to go ahead and just create our node class right now. So I'm just going to go ahead and add a new item, just a node header. So I'm just going to call it node.h. Get rid of the pragma once, and then I'm going to do if and def node h, define node h, and if, and then we're going to represent our node as a structure. I think we did a little bit of this with our dictionary. Let me see if I can pull that code up. Where we represented each letter as a node, and so we had a node represented as a structure, and we essentially had an array of children. So it's going to be somewhat similar here, where we have a property in the node, which will be the name, and then we're going to have not an array of children, because the number of children and the number of neighbors that this node has varies. So we're essentially going to use a vector to store it. So yeah, that's where we used some nodes before. So like I said, we're going to use a vector, so we have to include vector here. And then we're going to create a node structure. So the way we're going to do this is type def struct node, and then we're just going to put node down there. And all this does is essentially tells the compiler call structure node, just as node. This is usually typical declarations for structures. Alright, so the first property we're going to have is a name, so const char star name, and then we're going to have a vector. So the vector will hold two things. It's going to hold a node and a double to represent the weight between this node and its neighbor. So we're essentially going to have a vector of pairs. And you might be wondering why not just use the dictionary. Well, we could, but it won't be as easy to iterate through. So we're just going to use a vector of pairs for now. So we're going to say std vector std pair, and it's going to hold a structure node, a pointer to it, and a double. And we're just going to call this neighbors. And we might also be wondering why we're calling it struct node. We well, the compiler reads it from top to bottom, so it doesn't know that struct node is called a node yet, because it's still reading through the structure. If we put type def struct node node here, we would be able to, but we don't need to. So we're just going to call this struct node for now. Alright, next we're going to have a couple of methods. We're going to want to override some of the operators, because if you remember the algorithm, we're going to have to test if distances are less than or greater than, and we're also going to have to test to see if two nodes are even. So we're essentially going to use the operators and test the names or the IDs. So in a program, the names would have to be the IDs of each node. So what we say is operator equals, and we're going to pass in a const struct node, a reference to that, and const. And this is just typical parameters for an operator overload. And then we're also going to have a not equal, so bool operator is not equal, and we're going to say const struct node with that, and then we're going to have a method to actually retrieve the distance between this node and the node, and double distance to the node, and this will go in this method. Find the node and then last, we're going to have a static generator method, just to make things a little easier in the main class or the main file. So all it's going to be is a static, and it's going to return a pointer to a struct node and gen node, and we're just going to pass in a name. So const char star name. Let me actually just check. I'm going to go back right to this screen in a bit. I just need to check something real quick. How do I... Alright. Alright. So yeah, these are the methods that we'll have to be writing, and then we will write them right now. So, once you have all these done, we can go ahead and create a new source file. This will be the last file that we'll be creating today. It's just going to be node.cpp. The first line is just going to include the header, so include node.h. And then we're going to override our operators first, so we can actually just copy down the definitions just to make things a little easier. Just make sure to remove your static, not like that in a source file. Alright. And get rid of your semicolons as well. Okay. So let's go through the equals first. Also, last thing I forgot to do was remove the struct there, and then just include your identifiers up here. So node : because then the compiler doesn't know that this is a part of the node structure. Alright, so in equals, we're essentially just going to say return the name of this structure of this node is equal to n.name. So n is the node that we passed in. Likewise, for the non-equals, we're essentially going to say return name is not equal n.name. Alright. Now, for the distance, like I said, we're going to iterate through each of the neighbors. So we're going to go ahead and say for standard pair of a node pointer and a double pair in neighbors. If pair.first is equal to n. So this is once again going to this is using our operator overloaders. We can actually The one thing that I did run into when I was testing this is you can't really use this. You have to dereference it. If you try to overload an operator with a pointer, it's not really going to work. So you essentially have to pass in a reference, but if you pass in a pointer, it won't work. So you have to dereference the pointer and then pass in a reference to that. It's kind of weird, but that's how it's going to work. All right, and okay, so if the two nodes are equal, so if the pair that we're at if that neighbor has the same node, then we're essentially just going to return pair.second, just like that. All right, now for gen node, it's going to be relatively simple. All we're going to say is just node pointer ret is equal to new node, and then return name is equal to name. And remember to use your pointer operators there because ret is a pointer, and then we're just going to return ret, just like that. Okay, now that we have our node stuff done, we can go into main, and we can go ahead and I'm going to delete a couple of things. Or I won't delete yet, but we will eventually. So we're going to go ahead and include our node header. So include node.h, just like that. I'm actually going to go ahead and skip. Here we go. All right. I'm actually just going to... Shit, what do I want to do? Oh yeah. So let's go ahead and we can leave the contain. So let's go into our main method, and we're essentially going to delete everything except for the hello world statement and the return statement. So now when we run it, all we should get is just hello Dijkstra. Oh, here's this. That returned. So hello Dijkstra. Even though he's dead, right? Dijkstra. No, I don't want Dijkstra. Oh yeah, he died 18 years ago. 2002 was a long. Holy crap. I just realized that's a really long time ago. Damn, time goes flying. Alright. Okay, so essentially what we're going to do is instead of having, I'm going to go back to the image, and instead of having the array, we're going to create a different node structure for each of these nodes. So we'll have a total of 7 nodes. It's going to get a bit tedious, but it's going to work out. Alright, so we'll start with node A. Node pointer A is equal to node gen node. We're going to use that static method just with the name A, just like that. And I'm just going to copy this and paste it 6 more times. 1, 2, 3, 4, 5, 6, and then I'm just going to change the name. B, C, D, E, F, and G. B, C, D, E, F, and G. Alright, now to set the neighbors, we're just going to do an assignment right here, and what it's going to look like is A neighbors is equal to, and we're going to use an initializer list here. We looked at this in our JSON parsing algorithm. So essentially, all it is going to be for a vector. You're just going to initialize it using brackets, and you're going to separate each element with a comma. And then because we have pairs, we're also going to include a B. So for A, there are 2 neighbors, B and C, and B is a weight of 5. So the way we're going to represent that pair is just a B, comma that. And then for the C, it'll just be C, comma 3, and that'll be it. Okay. And then I'll also copy this 6 times. 2, 3, 4, 5, 6, 7. And then I'll put the names down. Damn it, stop. No, damn it, god damn it. Alright, I guess it's... I'm not even spelling right. E, D, why can't I go backwards? Okay. F has no neighbors, so we can get rid of that line. I just have this code down already, so I'm just gonna... You can do this by yourself if you want, just... So like I said, A has 2 neighbors, C and B. B is a weight of 5 just from this number, and C is a weight of 3 just from this number. Let me actually put this in the description real quick. Might already be in there. I don't know. So it is in the description now. Alright, so let's just go through the neighbors. So B has 3 neighbors, C 2, E3. Hold on. E3. I'm getting distracted again. Oh my god. E3. There we go. Wasn't E3? Yeah, E3 was canceled now. That's what I thought. Damn it. That's sad. E3 and then G1. So the way we're going to represent that is just in curly braces G, comma 1. And remember, these letters over here are just representative of the nodes over here. Oh, this fucking song slaps. I actually have been lacking in listening to this soundtrack for a bit, but you know what? It's good that I'm listening to it now. Okay. C has 2 neighbors, E and D, and they both have a weight of 7. D has 2 neighbors, A, and A is 2, and F is 6. Not FG. F is 6. E has 2 neighbors. Let me turn this down a bit, actually, it's kind of loud. Even though it's a great song. D, 2, and F, 1. And G only has 1 neighbor because it's lonely, and that is just an E1, although it is near to E, so that's good. Okay. So, we're essentially going to use all of the same methods that we used in the last video, except we're just going to replace them. So what I'm going to do now is I'm just going to create a new file. I'm just going to put it off to the side. And I'm just going to put all the code that we have. Actually, just going to zoom out a bit. And I'm going to delete everything that we have except for the main method. You can also get rid of the print array methods; those are not going to be used. And then, lastly, I'm going to put all of these methods in the Dijkstra namespace. So what this is going to, let me just start. So delete everything but the contains method and the main method. You can also delete the define, and you can also delete the limits include. So we're going to define the rest of our we're going to define the rest of our methods in our namespace. So I'm going to call it namespace Dijkstra. I'm just going to go ahead and put this off to the side. Alright, so first method is find min on q. Last time it returned an integer for the index in the array of neighbors that we had, or in the array of nodes. This time it's just going to return a pointer to the node. So node star find min on q, and we're going to pass in the q. So standard vector, standard pair. Last time the q was just a, if I'm right, the q was just a vector of a pair of an integer and double, but once again we're replacing integers with nodes. In this case, so node star comma double, and we're just going to say q. Int find on q. This is just going to be finding the index, so it's just going to be standard vector, standard pair of node pointer and double, and it's going to be the q, and then we're going to pass in the element that we want to find. Next is we're going to have two calculate distance methods like we did here, and they're both going to return double. So double calculate distance. The first one is going to be from, it's going to calculate the root distance from one thing, from the start to the finish, and we're essentially going to use this in determining the queue and determining the shortest paths tree. And the second calculate distance will be, given the shortest paths tree, calculate the shortest distance to the goal. So we're going to have standard map of a node star and a double. This will be for the weight. We're going to have a standard map of a node star to a node star, which will be previous node. And then the last one will be, last parameter will just be a pointer to the specified element. And that's pretty synonymous with what we have over here, because this double, the weight array that we had was a double array. And essentially what we're doing here is, instead of mapping an integer to a double, which we do in an array, is we're mapping a node to a double here. Alright, and then the second calculate distance method, calculate distance, and we're going to pass in the shortest paths tree, which will actually just be represented as a node, because essentially if we look at the shortest paths tree, where is it? It's right here. It starts at one node and it has a bunch of neighbors. So essentially we'll be representing it with one pointer, and that'll be the shortest paths tree. And from there you'll be able to get anywhere. So node shortest paths tree and node goal. Alright, last one, we'll be needing two more methods. Next one is just a node star. It returns a node pointer, and we're going to call this generate tree. This is going to be a recursive method that, let me actually just try and explain this a little bit. This will be a recursive method that we'll be using to generate the shortest paths tree, because it's not as easy to actually backtrack. Because with the 2D array, we essentially just mapped indices to weights. But here it's not as easy because we don't have an array where the indices are matched with the nodes. We just have nodes. We don't have any indices. So we're going to essentially have to recursively find different nodes. So that'll be a method that I'll walk through. So we're just calling generate tree, and it's going to take in the weight, the previous node, and then the specified node. So standard map of a node star to a double, weight, standard map of a node pointer to a node pointer, previous node, and then the specified node n. N will essentially be the root of this branch of the tree. So I'll explain when we get there. Alright, and then the last method will just be the general method, node pointer algorithm. And it's love the nether music. I'm just not looking for that right now. I don't know. Okay. Here, let me just send a quick text real quick. So yeah, anyway, hope you guys are all doing well. I am not in quarantine yet, but you know, that could change. I am doing remote learning, as I think everyone is. So that's why I have this time now. Although my whole family is home, so it might not entirely affect my typical schedule, because even though I do have time, I do have to work around my family too, so they're not barging in on me. But you never know. Okay. Let me just finish this up. Alright. Okay. So let's go ahead and start writing the methods. So I'm just gonna go ahead and copy all the definitions down below. So in the main method, we can just go ahead and just write out what we're actually going to be using is, and all it's going to be is just a node pointer tree is equal to Dijkstra algorithm A, because A is our starting node. And then if we want to test it, we're just going to go ahead and say print out the distance, so Dijkstra calculate distance of the tree to node D, and we're just going to end the line. I hope that works. Why is it not? Did I mess something up? Oh, that's why. Because I didn't put the identifiers. Yeah, just make sure you put your identifiers in front. So the Dijkstra colon in front of all your methods. if you guys want a full in-depth tutorial on why all this code works, I already did this in a stream a couple weeks ago, so I would go check that out if you don't know what we're doing. Alright, so the biggest difference that we'll have between this algorithm and the one that we wrote before is that instead of initializing the entire table at once, we're going to have to construct upon it at different times. So as we go through the neighbors, we can't just put all of them as 0 right now because because this is built to be dynamic. We don't know how many nodes there might be. There's no, and we don't have all the names at this point. We'll only get the names once we get through all of them. So all we're going to be doing is we're just going to have it dynamic right now. All right, so what we do know is weight from the start is 0, and previous node from the start is equal. Oh, I'm writing this in the wrong method. That's why. Don't put this in the find min on queue. Put this in algorithm. And then previous node at start is equal to start. So that is essentially just all we did over here. So the distance from the source to the source is 0, and the previous node is the same thing. All right, we're gonna have our visited log. So standard vector of node pointers is visited, and this method that we wrote up here, this will hold because it's a template. So this will hold if we input a type name of node. Okay. So visited. Next, we want to have our queue. So a standard vector of a pairs of a node pointer and a double for our queue. And then we're just going to say queue.pushback. And we're going to use our initializer lists again. So start, comma 0. And that's essentially here, like we did. And then we're going to go into our loop. So while queue.size is not equal to 0, we're going to find the smallest element. So node pointer smallest is equal to find min on queue. This is going to be a method that we'll write in a second. Find min on queue, and we're just going to pass the queue. That just put a halt in my adrenaline right there. Holy crap. Yeah, man, that just... So once we get the smallest one, we're gonna push back the smallest. So visited push back. So we're gonna put the smallest one on the visited array. Once again, I did all this in one note. I did this by hand before, where we went through the actual process. But once again, watch that video if you want. All right, so push back the smallest, and then queue.erase. And then we're going to say queue.begin plus find on queue. Queue. I can't spell Q because it's literally the letter Q, but it has like 15 freaking letters after. Fuck. Oh my god. And smallest. Okay. So what this does is it gets the initial index. I don't know why the vectors have to do this, but it uses an iterator, not an integer. So the initial iterator plus the index of the smallest element. Don't worry about it. All right. Next, we're going to iterate through neighbors. So go through neighbors. So for standard pair of node star, node pointer and double neighbor in smallest. God, this fucking vlog's up shit. Oh my god. Hopefully you guys can't hear it because they've been working for 10 minutes now. It's kind of annoying, but as I love dogs. Come on. Oh, shut up. Alright. Next thing we want to do is node star location is equal to find on Q. Now that's the Q and I. Wait, no. What the hell am I doing? Find on Q, Q and neighbor dot first. What am I doing? Am I doing this right? Find on Q. Hold on. I think I screwed something up. No, this should not be a node star. The location should not be node star. It should be an integer. I'm sorry. I'm messing things up. Alright, so in the other for loop, in the one before, we had 4 if statements. But because we know that this neighbor exists, because it only has a limited amount, this weight will never be 0. So we're essentially going to say, we're going to get rid of that if statement, and all we're going to do is if contains, so, and the node this time, if the visited vector contains neighbor dot first. So if it's already been visited, we're essentially going to go ahead and continue. Oh, make that a node star. If you guys are really just disappointed with all these typos, head on over to Coding Babes, which will actually help you a lot more than me, especially because they give you a wide array of tutorials, like if you're an Android version, or if you're an HTML version, or a CSS version, or just a programming version in general. But if you are, go ahead and do this, and take these quizzes, because they'll really increase your testosterone. But let me see. Boy, I can't see. Which one is it? Is it 2? If I get this wrong, I'm actually going to be really pissed. That is correct. Yes, it's correct. This is true because of the title. Which part of the HTML page do search results remain? Title again, and then body. Too much. Can't even contain myself. Oh, fuck. Alright, let's keep going. Yeah, go head over there. Just head over there. Alright. Next if statement, else if location does not equal -1. So if it's in there, so in queue, find new path if necessary. So we're going to get the current distance like we did over here. So it's going to return double. So double current distance is equal to calculate distance of wait, previous node, and then the node. So neighbor dot first. Neighbor dot, I didn't explain this. Neighbor dot first is the node of the neighbor, not the double wait. Just the node. And then we're going to calculate the new distance. So double new distance is equal to calculate distance from a wait, previous node, and smallest plus smallest distance to neighbor dot first. And that's essentially the same thing that we did over here, except we have to retrieve the weights in a different way, like I said. All right. So once again, we're going to have to compare the distances. So if new distance is less than current distance, we're going to accept the path, and we're going to erase the element, so q dot begin plus location, and then we're going to push back the new distance, so q dot push back neighbor dot first, and then a new distance, and then we're going to say wait at neighbor first is equal to smallest distance neighbor dot first, and then previous node at neighbor dot first is equal to smallest. Didn't I didn't want to need another. So I'm jumping off voice, I'm sorry. I did a slot. This is essentially what we wrote over here. I'm just updating for the node class. There's a lot of good stuff. All right. And otherwise, last if statement, I'll just add it to the queue. And it's essentially going to be this. So we can actually just copy that. So we just assign the weight on the previous node. And then we go ahead and push back, q dot push back. We're going to put the neighbor dot first, comma, calculate distance from wait, previous node, and neighbor dot first. And then if I'm right, plus, oh no, it's just that. Alright, so that's the loop, and once we've iterated through that, now we can go ahead and generate the tree. And we're just going to go ahead and actually just call this method 1, so node shortest paths tree is equal to generate tree from wait, previous node, and the start. And because it's recursive, we only have to call it once. We don't have to do anything else here. This is kind of easier, but it's not as practical, like I said. And then we're just going to go ahead and return shortest paths tree. Alright, that was the easy part. Now for updating the other methods. Let's start with find min on queue. So it's going to look pretty similar to what we have. I need to find it. It's going to look pretty similar to what we have. So we're going to have a min and a return placeholder. So double min is equal to q dot at 0 dot second. This gets the first weight, and then the return placeholder will just be the first node. So q dot at 0 dot first, and then we're going to iterate through the q. So for int I is equal to 1 because we want to start at the second element. Size is equal to q dot size. I is less than size, I plus plus. And we're going to say if q dot at I dot second is less than min, we have found a new minimum. So found new min. This is just basic minimum discovery. So min is equal to q dot at I dot second, and then we just update the return placeholder as well. So ret is equal to q dot at I dot first, and then we just return ret. All right. Next method is find on q. This is going to look pretty similar. We're essentially just finding the index, and it's actually going to look the exact same. So I can actually just, I'll just walk through it again. So we're going to have the same for loops of for int I is equal to 0, comma, size is equal to q dot size, I is less than size, I plus plus, and then we're going to say if, and this time we have to use our dereference operators because once again the comparison requires that it be dereferenced. So you just dereference by putting the asterisk in there. So q dot at I dot first is equal to a dereference of element, and if it is, we just return I. Otherwise was not found, so return -1. All right, hopefully, yeah, that all works. All right. For calculate distance, it's going to be pretty much the exact same. So once again, we're going to have to dereference stuff. So if previous node at element is equal to dereference of an element, distance from element to self is 0. So we're just going to return 0. And otherwise, we're going to return the weight of the element in the weight table. So return weight at element plus calculate distance of weight and previous node, but to the parent of this node, so previous node at element. So the node that points to this node right here, and this is pretty much the same as what we've written before. All right. Next, calculate distance method. Let's actually get to that later. Let's just do the generate tree first. All right. So generate tree. The way I thought about this was we essentially have to go to the end of each branch and see if it, or here, let me just, I did not comment my tests. Here, let me just kind of work through this. So I create a return placeholder, so node return is equal to node gen node with the same name. So in our class, these ret and end are going to be equal. The only difference is we want to create a new node because in our shortest path tree, we don't want to have every neighbor of that because each path might not be as efficient. So we want to create a new tree like this. We want to create an entirely new tree, and it only has the neighbors that are along the shortest path. All right, so return just like that, and essentially we're going to iterate through each neighbor. Hold on, let me just. Okay. So we're going to iterate through each neighbor. Here, so let me just do this. I'm sorry. So for standard pair of node pointer to node pointer pair in the previous node. So in each neighbor, we want to see if the previous node of that neighbor, Wait, no, we're not iterating through each neighbor. We're iterating through each thing of previous node. Because we want to see if I'm sorry. All right, I got it. So we're iterating through each element in the previous node, and we're seeing which elements, which nodes come from this node. Because in a shortest paths tree, each element only has one path pointing to it. You can have multiple paths coming out of it, but only has one path going to it. So in each, so previous node will have one unique path to it. So for pair in previous node, we're going to go ahead and say if a dereference of pair.second is equal to a dereference of ret. So if the pair, if previous node, if the element if the current element in the previous node has a if the element that we are currently on in the previous node array, if that has a parent of the current node that we're at, then we know that it's pointing. So we know that I'm really sorry. Okay, let me actually just write this out. Don't listen to anything I just said. And pair first does not equal ret. Node. Alright. And then at the end we return ret. So this is going to be our cursive method. And essentially all it says is we iterate through the previous node array and we find everything that has a parent node of the current node. So if we started with A, we would iterate through each of these elements and we would find the elements that have a previous node of A, which is A, B, and C. And this does not equal statement just means that it can't be itself, because in that case it would have a neighbor of itself in itself, and it would just be an infinite loop because it would keep going back to itself. That would account for this case A to A. But for B to A, or A to B, I mean, we're going to generate a new tree starting at B, which will be its own path. So we start at A, we look at B, B has B's previous node is A, so B, and then so we'll generate a new tree for B, which will contain G, E, F, and D, and then we will also go through the next element, which will be C, which also has a previous node of A, and we'll just put that there as a neighbor. And because C has no previous node over here, it's not going to have any neighbors in the shortest paths tree. Hopefully that makes a little bit of sense. All right, so the thing is, it's a recursive method. That's all that matters, really. All right. All right, last method is calculate distance. All right, so this one is going to be kind of annoying because it's gonna seem really inefficient, but it'll make a little bit of sense. So the first thing, or let me actually just draw this out. So the way I thought about this was, let me bring the shortest paths tree over. Alright, so I can bring up my drawing pad. Oh, come on, what's going on? Alright, so it's right there. Alright, so we start at A. wanted to get to a goal of C. So essentially what we're going to have to do is, because we can't really backtrack from C, because C has no recollection of what points to it in the shortest path tree, we're going to have to go recursively from the start, or not recursively. We're going to have to just go through all the neighbors of A and see what happens. So A neighbors, or first actually, A does not equal C. So we go through A neighbors. B does not equal C. So then we go through B neighbors all the way to the end. And when we find that F has no neighbors, or D, F have no neighbors, we start returning -1. So return, and that will return -1 all the way to B. So when we get to B, we find a -1 there. And then now we get to C, and C is equal to C. So we add the weight from A to C, which is just 3. Let me give you a more complex example, or the way I thought about this. Let's say our goal was, we have a goal of F. So we go through A neighbors. B does not equal F. B neighbors. So I'm just going to not write neighbors every time. G does not equal F. So G neighbors. E does not equal F. In E neighbors, D does not equal F. So we return -1. But F is equal to F. So we return the weight is, and it's 1. Let me actually just write the weights here. So we have a 1, 2, 1, 5, 3. So F is equal to F, so we return a 1, and that goes back to E. And so if E determines that it did not return -1, we add the weight of E. So it goes 1 plus 1 is 2, which goes back to G, which goes 1 plus 2. And then to B, which is, am I doing this right? No, I'm not doing this right. F returns 1. Or F returns that it found something. So that returns a 1 to, or that returns a true to E. E returns a 1. Then G returns a 1 plus a 1. And then B returns a 1 plus 2, the previous one, so a 3, and then it goes back to A because it found something, and that returns a 5 plus 3 is equal to 8, which is our final distance. So that's the way I thought about it. This is going to be a lot of recursion, but luckily we've done a lot of recursion in all these challenges, so it should not be that big of a challenge. So in calculate distance, I can actually get rid of this text file because we don't need it anymore. So in calculate distance, we're gonna have to test to see if the two nodes are equal. So if a dereference of shortest paths tree is equal to a dereference of goal, or returning 0. Next, we're gonna have a placeholder for the return weight. So double ret is equal to. No, we actually don't need that. I'm sorry. We don't. Oh, what did I delete? In our default case, we return -1. And a double pair in shortest paths tree neighbors. We're going to calculate the weight from the neighbor to the goal. So we're essentially going to call this method again. So double W is equal to calculate distance from this node, so pair dot first, to the goal. If W it does not equal -1. So if it found something when w is equal to -1, it didn't find something. But if it's not equal to -1, like over here, f returned a 1, so that means that it found, or f returned a 0 because it found something. So yeah, it found something. So that means that so that means add it to the weight. So all we're going to do is return shortest paths tree, distance to this node, so pair got first, or this neighbor, plus a w. It's kind of weird, but don't worry about it. It'll all make sense. We can actually just go through a debug of this. All the other stuff we've pretty much done, which is the same as before. So I'm actually just going to create a breakpoint over here. And let's say our goal, what did we say our goal was? F. So we should get an 8. Let me actually just disable this breakpoint just to make sure everything works right now. Alright, so our first run, and we get 8. Good. Alright, so now let's go through the debugging of it, just so I can kind of walk through it. Alright, let me actually just check something real quick. So, debug. We have our shortest paths tree, and let's go into this method here. Alright, so our current, our starting node right now is A. So A does not equal F. So then we go into the neighbors of A. So the current pair that we're working on right now is pair is C. So we're going to see if W does not equal -1. Well, W return, or did return -1 because C did not find it here. I forgot to go into it, but you'll see. All right, so let's go into this method here. Now we're at B, and B should find something because we're there. So we go through the neighbors of B because B does not equal F. So go into this one, we're looking at G, just like that. So G does not equal F, we keep going into there. E, hold on, let me just make sure. E, okay. So we're looking, the next pair will be D, so now we're looking at D. D has no neighbors. So therefore we just return -1 as a default case. And when we get back, we see that distance from, or the calculated distance for the D returned -1 because it didn't find anything along that path. So now we go to the next neighbor, which is F, and F returns 0 because F is equal to F, which is right there. And because of that, we return the distance from E to F plus W, which is 0. So then we just keep going back through. 2, 3, 5, and then 8. And we're done. Perfect. Woohoo! We did it. That was longer than it had to be because I did not know what to type, but hold on, let me just play a banger song real quick, even though I love this. Let me just go hit a banger. So yeah, that's pretty much it for today. Just a quick recap, we created our node class, which is similar to node classes that we've created in the past, like for the dictionary. And this can be used in a lot of places, and we're using it in Dijkstra's algorithm now. We updated all the algorithm code to match this new thing. We looked at a whole bunch of recursion. We had, let's see, we had one. Let's see how much recursion we had. We had the generate tree, calculate distance the second time. We had 3 instances of recursion, which is a lot, especially for an algorithm with only like 6 methods or something. But it's a lot of good practice there. Yeah. I actually have nothing else to talk about. Yeah. So you see, if you had a map like in Plague.inc or something, and can I make this joke? Ah, fuck. I don't think I. All right. I'm gonna spare the joke. It's getting too serious. It's not meme worthy anymore. It's too serious to make memes about. I'm gonna make it either way. So if you did have a map in Plague.inc and you were trying to spread a virus, maybe named after a beer company, maybe not. That's left up to interpretation. Just if it was, let's say, and you were playing Plague.inc and you, God, I can't talk, and you created an AI to play Plague.inc, and you wanted to calculate the fastest distance from China to America. Like let's just say that the virus originated in China, and then it got to America just somehow. And you know what? You did it using Dijkstra, so congratulations. You just created a world pandemic that's devastated billions of people, put a lot of people at home, quarantined a lot of people. But you know what? It's what happens. It's nature. I actually should stop talking before I get myself in trouble. Oh God. Oh, I might have the CDC knocking on my door in a bit, but okay. I'm done. Yeah, that's all I have for you guys today. Yeah. Goodbye.